You were told entropy means disorder. A clean desk becomes cluttered. Glass falls and shatters. Cream swirls into coffee and never undash swirls dot, so you conclude. Entropy is the universe's preference for mess dot. This is wrong. The problem begins with your eyes. You look at a neat stack of papers and call it ordered. You look at the same papers scattered across the floor and call it disordered. But physics does not see stacks or mess. It does not recognize desks. It does not recognize paper. It does not recognize neat. Physics sees positions, momenta, molecules, nothing more. Take that shattered glass. You see destruction, irreversibility, loss of structure. But zoom in far enough, down to atoms obeying the same mechanical rules before and after the fall, and nothing about those rules changed. No new law activated when the glass hit the ground. No entropy force switched on. The atoms simply moved. Before the fall, they were arranged in a tight lattice. After the fall, they were arranged in fragments. To you, one arrangement looks meaningful. The other looks ruined. But that meaning exists only in your scale of perception. Now, imagine freezing time at the atomic level and taking a snapshot. Just coordinates and velocities. No labels, no story. Just numbers. Which snapshot is ordered? There is no answer inside the physics itself. You think disorder is more random. But randomness is not something you see. It is something you infer when you stop tracking details. When you lose information about exact configurations, you describe the system more crudely. And that coarseness, that ignorance, is what you call disorder. Entropy is not a measure of mess. It is a measure of how many microscopic ways there are to arrange something without you noticing a difference. That scattered glass feels disordered because there are many microscopic arrangements that still look like broken glass to you. Slightly different fragment positions. Slightly different atomic jitters. You would never distinguish them, but there are very few microscopic arrangements that look like a perfectly intact glass. Your judgment of order is really a judgment about rarity, and rarity has nothing to do with chaos. It has everything to do with counting. Already, the story shifts. Entropy is not the universe degrading into ugliness. It is not nature's preference for chaos. It is not destruction. It is arithmetic. And once you see that, the comforting narrative collapses. Because if entropy is about counting possible arrangements, then what you call order was never stable to begin with. It was simply outnumbered. You assume the laws of physics are on entropy's side. That's somewhere buried deep in the equations. There is a clause that says things must fall apart. There isn't. Take the laws of motion written down by Isaac Newton. Reverse the direction of time in those equations. Replace every velocity with its negative, and they still work perfectly. A planet orbiting a star forward in time obeys the same law as a planet retracing its path backward. The equations don't notice jump to electricity and magnetism. The field equations written by James Clerk Maxwell are also time-symmetric. Reverse the motion of every charged particle, and the mathematics remains intact. Nothing breaks, even in quantum mechanics. In the wave equation formulated by Erwin Schrödinger, the same symmetry appears. Reverse the evolution, and the equation does not protest. The microscopic world does not know which way time flows. So where exactly is entropy hiding? Not in the laws. Imagine filming two billiard balls colliding on a frictionless table. Now play the film backward. The balls approach, collide, and separate. Nothing in that reversed movie violates Newton's laws. It looks unusual, perhaps, but not illegal. Now imagine 100 billiard balls scattering after a break shot. Play that backward. They roll together, converge into a perfect triangular rack, and stop dot. This feels impossible, but the laws allow it. There is no equation forbidding the balls from assembling themselves. There is no physical principle that says fragments of glass may not leap from the floor and fuse midair into a pristine cup. If you could precisely reverse every particle's velocity, every atom in the room, every vibration in the air, the shattered glass would reassemble. Not approximately. Exactly. The microscopic rules would guide it back. This is the rebellion. At the fundamental level, nothing prefers the future over the past. Nothing pushes toward higher entropy. And yet, in your experience, entropy increases without exception. You never see the billiard balls spontaneously rack themselves. You never see smoke flow neatly back into a cigarette. You never see cream separate itself from coffee. Not one stop. So, now you are trapped. The laws do not enforce entropy's victory, but entropy wins anyway. If it is not written into the equations, then it must emerge from something else, and that something is not force. It is number. You look at a room and describe it in broad strokes. Air is warm. The coffee is mixed. Glass is broken. These descriptions feel physical, as if they are facts written into the world itself. But they are not. They are summaries. Compressed stories you tell because you cannot track every atom. Physics makes a distinction you rarely notice. There is the microstate, the exact position and motion of every particle. And then there is the macrostate, the coarse description you use because the microscopic details are invisible to you. The distinction changes everything. Imagine a box filled with gas molecules. If you could pause reality and write down the exact coordinates and velocities of each molecule, you would describe one specific microstate. Shift a single molecule by a fraction of a millimeter, and you now have a different microstate. From physics' point of view, these are completely different universes, but to you, they look identical. You still just say, a box of gas. That phrase hides an absurd number of possibilities. Now imagine the gas starts in the corner of the box. You remove the divider and the gas spreads out. You say entropy increased because the gas became more disordered, but nothing forced the molecules outward. They simply moved according to the same mechanical laws as before. The key is counting. There are very few microstates, where almost all the molecules sit neatly in one corner. There are unimaginably many microstates where the molecules are spread evenly throughout the box. When the system evolves, it wanders through microstates. It does not choose disorder. It simply moves. And because there are vastly more spread out states than corner states, wandering almost always leads outward. You were never watching order decay. You were watching a system move from rare configurations into common ones. This is the part that destroys. Intuition. You think a broken glass is fragile because it falls apart easily. But fragility is not the reason. An intact glass corresponds to a tiny subset of all the ways its atoms could be arranged while still looking like a glass. A broken glass corresponds to an astronomically larger subset. The difference is not stability. It is abundance. Imagine a library with one special book hidden among trillions of ordinary ones. Blindfold yourself and pick at random. You will almost never land on the special book. Not because it repels you, but because it is outnumbered. That is entropy. Entropy is a counting measure, a way of describing how many microstates fit inside a macrostate. High entropy means many possible microscopic arrangements. Low entropy means few. And now the word disorder begins to feel useless. Disorder suggests chaos, damage, meaninglessness. But entropy is neutral. It does not judge. It only counts. Feynman liked this ruthlessness. The universe is not trying to become messy. It is simply exploring configurations. And most configurations look ordinary to creatures like you. The unsettling implication is this: order is not something destroyed. Order is something statistically rare. And once you see reality as counting rather than breaking, the question changes again. If high entropy states are just overwhelmingly numerous, why do they feel inevitable? Why does probability begin to look like law? You still resist the idea. Probability feels optional. Laws feel unavoidable. A coin toss can go either way. Gravity cannot decide to stop. So when physicists say entropy is statistical, you imagine something soft, a tendency, not a certainty. But large numbers erase that distinction. Imagine flipping a coin twice. 2 heads is plausible. 2 tails is plausible. Nothing surprising happens. Now imagine flipping it 1 billion times. You still cannot predict the exact sequence, but you know something with quiet certainty. The number of heads will be close to half. Not because a law forces balance, but because the number of sequences that look balanced overwhelms the number that do not. Extreme outcomes are not impossible. They are simply drowned. Entropy works the same way, except the numbers involved are beyond intuition. A glass contains around 10,231,023 particles. That is not many. It is a number so large that your brain has no structure for it. With numbers this large, probability stops feeling like chance and starts feeling like destiny. Think again about gas spreading through a room. A single molecule could move anywhere. 2 molecules can arrange themselves in several ways. But as the count grows, the number of microstates corresponding to an even spread explodes. The number corresponding to all molecules clustered in one corner becomes vanishingly tiny by comparison. Not zero, just unimaginably small. If you waited long enough, far longer than the age of the universe, the gas could randomly regroup itself into the corner. The laws allow it. Entropy does not forbid it. But the odds are so absurdly low that you will never witness it. This is the brutal shift in perspective. Entropy does not rise because it must. Entropy rises because, in a sea of possibilities, nearly every path leads the same way. Imagine wandering blindly across a landscape where nearly every step slopes downward. You do not fall because gravity commands you. You fall because almost all directions lead down. To a creature living inside the process. That statistical bias looks indistinguishable from a rule, and this is why time feels one directional when you remember the past. You remember low entropy arrangements, structured states with fewer microscopic possibilities. As time progresses, systems move toward regions of phase space that contain vastly more states. The forward direction is simply the direction toward overwhelming numbers. You do not experience probability directly. You experience its consequences repeated without exception. So your mind invents a story. Entropy is a force. The universe decays. Time flows. But none of those are fundamental truths. What feels like fate is arithmetic, played on impossible scales. And yet there is a deeper wound in the logic. If the laws are time-symmetric, if high entropy is overwhelmingly likely, then why wasn't the universe already there from the beginning? Why did anything ever start in a low entropy state at all? That question is where physics stops comforting you. By now, you expect an answer that feels mechanical. Some hidden law. Some cosmic engine pushing entropy upward from the beginning of time. Instead, physics gives you something uncomfortable. Entropy increases because the past was strange, not slightly unusual. Extraordinarily so. If high entropy states correspond to overwhelmingly many microstates, then the most natural universe, the most statistically typical one, would already be in equilibrium. No structure, no stars burning, no gradients to exploit, no history unfolding. nothing happening at all. And yet the early universe was the opposite. Observations of the cosmic microwave background show that the young universe was astonishingly smooth, matter distributed almost perfectly evenly. Temperature difference is tiny, geometry simple. It looked ordered on a cosmic scale. That sounds like high entropy to intuition. Smoothness feels uniform, and uniformity feels random. This is wrong. Gravity changes the counting. In systems dominated by gravity, clumping increases entropy. A smooth distribution of matter is actually special because there are comparatively few ways to arrange mass without creating lumps. Stars, black holes. Gravity amplifies small differences, creating structure. The smooth early universe was balanced in an almost improbable way. Low entropy. Which means the arrow of time. Everything you call history depends on a boundary condition, not a law. The universe began in a rare state and has been relaxing ever since. Feynman emphasized this point with characteristic bluntness. If you ask why entropy increases, you are really asking why the universe started off so unlikely. The equations do not explain it. They simply evolve whatever initial condition they are given. Physics can describe the motion. It does not yet explain the beginning. This realization feels backward. You thought entropy was about the future, about decay, aging, loss. But the direction of time is actually anchored in the past. The reason eggs break and do not unbreak is not hidden in the egg. It is hidden in the history of the universe itself. Every local increase in entropy traces back to that primordial low entropy condition. Your memory works the same way. You remember the past because information was encoded as entropy increased. You do not remember the future because those records do not yet exist. Time's arrow is not an active process. It is a consequence of where the universe started, and this creates an unsettling inversion. The question is no longer, why does entropy win? The real question is, why was entropy once so low that winning was even possible? Physics has hypotheses, cosmic inflation, multiverse scenarios, deeper cosmological principles, but no definitive answer. Here, uncertainty remains honest. The most important feature of our universe may be a brute fact. We do not yet understand that, so entropy's victory is not inevitable in an absolute sense. It is inevitable given the starting point. We live inside a long statistical relaxation away from an improbable beginning. And that means something even more unsettling is true. What you call normal, stars, life, thought, meaning, may be the temporary byproduct of a condition that was never typical at all. You began with a simple picture. Things fall apart. Entropy wins. Time moves forward because the universe decays. Now the picture is gone. Entropy does not attack. Order. The laws do not push toward chaos. The future is not pulled by a force. What remains is colder. Imagine all possible arrangements of matter, not just the ones you see, but every microscopic configuration consistent with the laws of physics. Almost all of them look dull, uniform, inactive, thermally exhausted. The universe is filled with interesting structure, galaxies, planets. Minds wondering about entropy occupy a tiny, fragile corner of possibility. You live inside that corner. Feynman's explanation feels brutal because it removes intention from the story. The universe is not trying to do anything. It is not progressing toward ruin. It is simply exploring an unimaginably vast landscape of states. And the overwhelming majority of those states are what we call high entropy. Entropy wins the way a crowd wins against an individual, not through effort, but through sheer numbers. And time itself begins to look different. The past feels fixed and meaningful because it corresponds to fewer possible states. The future feels open because it contains vastly more possibilities consistent with the present. As the system evolves, it drifts into regions where distinction fades, where countless microstates look the same from a human scale. Your sense of flow, of becoming, emerges from that drift. Even your identity rides on entropy's rise. Memories are physical records. Thinking consumes gradients. Life exists by burning order into heat. Every moment of awareness depends on the universe not yet reaching equilibrium. You are not watching entropy destroy meaning. You are borrowing meaning from the distance between a rare past and a common future. And here is the philosophical edge. If the universe had begun in a typical state, high entropy from the start, there would be no arrow of time, no evolution, no stories, no observers asking why anything changes. The very act of questioning entropy is only possible because entropy was once low. This turns the narrative inside out. Entropy does not threaten existence. Entropy makes existence possible, but only temporarily. Eventually, the gradients fade. Stars exhaust their fuel. Matter settles into quieter arrangements. Not because the universe is dying, but because it is becoming statistically ordinary. And yet there is a strange calm in this. The laws remain reversible. The microscopic world keeps no record of direction. What you call the passage of time is not written into reality's foundation. It is a perspective born from imbalance. You are living in the slope between probability and inevitability. Feynman's brutal clarity is this: the universe does not move toward disorder. It moves toward what is overwhelmingly likely, and somewhere inside that vast arithmetic, for a short interval measured against eternity, patterns emerged that could notice the counting itself. For a moment, the universe became aware of its own statistics. And that moment is you.